Let us switch over to problem number 7. A tiny spherical oil drop carrying a net charge Q is balanced in still air with a vertical uniform electric field of strength 81 pi by 7 into 10 power 5 volt per meter. When the field is switched off, the drop is observed to fall with terminal velocity 2 into 10 power minus 3 meter per second. Terminal velocity has been provided to us. Given that viscosity of air as 1.8 into 10 power minus 5 Newton second per meter square, density of oil is 900 kg per meter cube, and G as usual is 9.8 meter per second square, then the magnitude of the charge Q is how much? That is the concept. Problem is looking a little lengthy, but a very simple way of dealing with the problem let us discuss. And here the very first option is given 1.6 into 10 power minus 19 coulomb. The second option is 3.2 into 10 power minus 19 coulomb. Third option is 4.8 into 10 power minus 19 coulomb. And fourth option is 8 into 10 power minus 19 coulomb. In fact, the correct option for this particular problem is D. That is the fourth option there, which is 8 into 10 power minus 19 coulomb. Let us first of all write what are the values he has provided us. What is the data? He said electric field strength is 81 pi by 7 into 10 to the power minus 5, that is 10 to the power 5 volt per meter. That's what has been given. So this is one value which has been provided to us. That is the electric field in which the droplet was first balanced in air. That's what has been given. And the drop's terminal velocity is given 2 into 10 to the power minus 3 meter per second. That is V terminal. I'm just talking about. Terminal velocity is given that much. Fine. What else he said? He said viscosity of air as 1.8 into 10 power minus 5 Newton second per meter square. 1.8 into 10 power minus 5. 1.8 into 10 power minus 5 Newton second per meter square. That is coefficient of viscosity of that oil. What has been used over there is given there like that. And he said density of oil also. What is the density of oil given? 900 kg per meter cube. That's the value given. And of course we all know the value of acceleration due to gravity as 9.8 meter per second square. This is the complete data what has been provided to us. Now let us check first of all what is the condition for that droplet to stay still in air. It's neither falling down nor going up. What is the concept behind, and when will that be possible? When its weight, which is acting in the downward direction, is compensated by the force that is acting on the charge due to electric field. That means you people can understand straight away, if this is the oil drop weight which is mg, now should be compensated by the force due to electric field, which of course is taken as EQ. That is the condition. So what you people should understand first of all, EQ now must be equal to mg. That is one condition we can take when the drop is at rest in air after the application of external electric field of strength this much. But what did he say immediately? When the field is switched off, then the drop is observed to fall with terminal velocity. Then due to viscosity, that particular drop is attaining terminal velocity. Then what must be the second equation I can write here? 6 pi eta r v is equal to mg. All of you can understand this is the equation which is called Stokes' law. In viscosity chapter, we have discussed about this, particularly in fluids. 6 pi eta r v. Here eta stands for coefficient of viscosity of air and r is the radius of that drop, and Vt, that gives us the terminal velocity with which that drop is now falling down. But at the same time, we all know pretty well mass into g, that is acceleration due to gravity, that is the weight. But can't you understand this one as 4 by 3 pi r cube into rho into g directly? What for I have written like this, you can understand weight is nothing other than volume into density into acceleration due to gravity. So what I can write from this one, from this I directly can think that r cube is equal to 3 mg by 4 pi rho g. From the same equation, you can now write r is equal to 3 mg divided by 4 pi rho g whole power 1 by 3. This value, I now write it over here. So this equation, I substitute in my second equation over here. What is it I will be getting? Then 6 pi eta r into terminal velocity. R you write that one. It is 3 mg divide 4 pi rho g to the power 1 by 3 into terminal velocity, that is equal to mg here. But what actually we want here is the charge. So first of all, what we should do out of this? We should simplify till we get the value of charge over there. That means what is this mg? Here we have mg, there also we have mg. So finalize mg in terms of these values. Substitute that one over here and simplify for the value of E or charge Q over there. So what can we write now? Simply you just write the cube of this entire value. Cube of this entire value means what? You can write 6 pi eta into terminal velocity whole cube into 3 times mg divided by 4 pi rho into g is equal to mg whole power 3. I have just taken the cube on both sides. Now you can certainly understand 1 mg cancels over here. So can't you just write what is the corresponding equation for mg over here now? You can simply write this one as mg is equal to root of this whole thing. What is that root of this whole thing now? It will now be 6 pi eta, this value of into V terminal, right, whole cube divided by, what is next here we have? This 3 comes over here and this one will be 4 pi rho g whole under root. That is mg. The moment you have got this mg value, we know pretty well from the first equation, this mg must be equal to EQ. From the first equation, mg must be equal to EQ. This is mg now, that you equate it to EQ. Then what is the equation we just want? What is the value we want here? Therefore, charge is equal to. What is the charge now? This one you can write 3 times 6 pi eta terminal velocity whole cube divided by 4 pi rho into g whole under root into 1 by e. That is the complete form of this charge equation. But certainly a little lengthy number, because we are taking up 2 different concepts here. One, when the drop is being stationary in air, what is the condition? That condition we have taken it as EQ and mg are supposed to be equal and opposite. And what is the second one? When the electric field is totally put off, that drop is now reaching terminal velocity in the downward direction. That means with whatever force it is falling down must be equal to its weight again. So what can we write now? mg must be equal to 6 pi eta r into terminal velocity. Now we know what is weight, which is volume into density into acceleration due to gravity. From that I have calculated the radius of the drop. That I have substituted in the second equation. Therefrom I have estimated what is mg. That mg I have equated that one to EQ, wherefrom I can calculate the charge now like this. And all the values are provided to you there. The value of electric field strength is given, terminal velocity is given, eta, which is a coefficient of viscosity, that is given. Acceleration due to gravity anyhow is 9.8 meter per second square, which we know even otherwise also. In addition, he gave the density of that liquid as well. What is the density given? 900. Now just substituting the values here, simplify the whole lot. Then you will be getting around 8 into 10 to the power minus 19 coulomb you get. The charge on that particular drop now becomes 8 into 10 power minus 19 coulomb. So if you look at all the 4 options given over there, 4th option is exactly in coincidence with this answer what we are getting. So we can say the key or the answer over here will now be this D over here now. But one thing you should understand, same model question has appeared in one of the papers earlier. But okay, you cannot further minimize the size of this, because this is one particular problem where we are having the involvement of 2 different concepts. One, the condition for the drop to be stationary in air. And second one, when it is falling down with uniform velocity, that is what is called terminal velocity in this particular case, what is the condition for its weight? So taking those 2, we are estimating the total charge on that particular drop as such. So certainly a little lengthy model, but roughly if you estimate the answers over there, the values if you substitute and estimate, certainly the answer can be estimated out of that. That is the concept. So correct answer for 7th problem is D in this particular order. So this is problem number 7, a little lengthier model of all what we have discussed so far. Now problem number 8. For the hemisphere of radius capital R shown in the figure, the surface charge density sigma varies with theta as sigma is equal to sigma naught cos theta. The total charge on the sphere is how much? That is the concept. He has given us 4 options once again. First option says 2 sigma naught pi r square. Second option is sigma naught pi r square by 2. Third option is sigma naught pi r square by 3. And fourth option is sigma naught pi r square. And out of all the 4 options, the fourth option is the correct one for us. For the hemisphere of radius r shown in the figure, the surface charge density sigma varies with theta as sigma is equal to sigma naught cos theta. So this is the hemisphere what has been mentioned in the problem. You can all understand this one is going to be the radius over here. As usual, we can take up the charge on this hemispherical body is positive like this. It is given in the problem. And of course, this radius is given as r. For doing the problem, what we people have to think of? It is a spherical body. So what we do is, we consider a small circular ring over there on its surface. That circular ring, in what sense we people are taking up? That circular ring is going to have a thickness dx. At the same time, when I just take here, what is the value of the angle these two ends are making with each other? This angle, I take it as d phi. And of course, the total value over here, the thickness as dx, the small element we people are considering over here there. Now, what is the relation? Sigma is given sigma naught cos theta. That is what has been given to us. So let us first of all write, what do you mean by surface charge density? So surface charge density sigma can be written as dq by dA. A is going to be the area. So what can we write now in this case, please? dq by 2 pi r into dx I can write. That is of this element which is circular by nature, what we people have considered. That is important. So you can understand this one now. dq is equal to sigma into 2 pi r dx. But you can understand directly, sigma is given sigma naught cos theta. So let us write that one. Sigma naught cos theta into 2 pi r into dx. That is dq now. But you can certainly understand what will be this dx now. Can't you write that one as r into this angle, that is d phi there? So we can write that one directly as r into d phi. And this angle, let us take this one as a theta. So what is it you people are going to get now? If I just take this angle in terms of theta as d theta, then I directly can write, but dx is equal to r d theta. Directly you write that one here. dq is equal to sigma naught cos theta into 2 pi r into r d theta. That is the concept. Observe carefully, from this particular triangle, this is opposite side, this is hypotenuse, and this one is adjacent side. What will be the value of sin theta out of that I write? Look at carefully, sin theta here is opposite by hypotenuse. So what can we write now? But sin theta, that can be written as r by r. So what else I can write from this? Small r is equal to capital R sin theta. This value you substitute in place of small r. Then what is it you are going to get? You see now, dq is equal to sigma naught cos theta into this 2 pi into small r. What is that small r? R sin theta. So 2 pi r sin theta into what next we have? R d theta we have. That r into r square d theta like. Now just look at carefully. This can be taken as 2 sin theta cos theta. That can be written as sin 2 theta. So what is that equation we are going to get now? Sigma naught will be as it is, pi will be taken as it is, r square will be taken as it is. Then 2 sin theta cos theta, that now becomes sin 2 theta into this d theta as usual. You will be getting as dq. What is it I want? You all know. We want the total charge on the system. So what can we do now? We just have to integrate. So this implies charge q is equal to integral between 0 and pi by 2. You directly can write like that. What is that value given? Sigma naught pi r square sin 2 theta d theta. Sigma naught is constant, pi constant, r square constant, sin 2 theta d theta, that now becomes minus cos 2 theta by 2. In between the limits 0 and pi by 2. That is the concept. And you can certainly understand it too. You can bring it out now. So what is now going to be the result? It is now q is equal to sigma naught pi r square by 2. Till that extent it is okay. Now cos 2 theta, that too with a negative sign. Theta is pi by 2. Cos 180, it's now minus 1. So what happens to this one over here? This becomes 1 plus 1, it now becomes 2. That is the concept. So overall, this 2 gets cancelled. So what is left over? Charge on this one is sigma naught pi r square. This is the actual charge. And which particular option that is coinciding with this answer? Look at the options. Fourth option is exactly the same thing you are getting, sigma naught pi into r square. That is the concept. Therefore, I can take the answer for this one as D. That is the case you have to remember. So once again, what we people have done, let me just give you in brief. This is a totally hemispherical body, a solid body. Therefore, we have imagined a small circular ring of thickness dx over there, having radius r. So based on that one, I have calculated the surface area of that ring. What is that surface area? 2 pi r into dx. That I have substituted in this formula. After getting that, what is dx? Dx is r d theta. I have substituted that. And what is the relation between small r and capital R? I have taken up. What is the relation between them? Sin theta is equal to small r by capital R. Then small r can be written as r sin theta. That you can substitute here. After that, we have just written sin 2 theta in place of 2 sin theta cos theta. Then we have integrated between 0 and pi by 2 from the midpoint to the end, that's 0 to pi by 2. What is that value we have obtained? You look at sigma naught pi r square. That is in coincidence with the fourth option for us. Thereby, the correct answer for this problem is D. So this is equally a very good model for us. Same question has been given earlier in one of the JEE papers. So try to understand the concept carefully and remember that one thoroughly. So this is problem number 8 what we have. Let us take up problem number 9. One of the excellent model questions what we have. A simple one. But one should understand what exactly that is happening over there carefully. Two identical beads having a mass m and charge q, when placed in a hemispherical bowl of radius r with frictionless and non-conducting walls, the beads move and at equilibrium they are at a separation capital R as shown. The charge on each bead is how much? 4 options once again he has mentioned. First option is square root of 4 pi epsilon naught mgr square by root 3. Second option is square root of 4 pi epsilon naught mgr square by 3. Third option is square root of 4 pi epsilon naught mgr square by root 5. And fourth option is square root of 4 pi epsilon naught mgr by 3. So out of all the 4, the correct option for us is the first option. That is A, which is 4 pi epsilon naught mgr square by root 3 whole under root. That's the point. What is the figure he has provided? Look at that one. This is the figure he has mentioned. There is one bead here and one more bead here. Now this is actually the case. The distance between these two is given as r like this. And it is a spherical one, a hemispherical one. So this way he has mentioned. And you can understand well, this is going to be the diameter of this particular spherical shaped hemispherical one. So if you look at this one, there are two beads what he is talking, one is A and one is B. And this distance he has given it as r. This distance also is r, this one also is r, because you know each one of them will be the radii or radius of that particular spherical body. So if you look at carefully, this is r, and this is also given as r. So can't you just understand this particular system is giving you an equilateral triangle over there? So if I just draw the same concept outside like this, you can say that this is the one. You are finding one bead here, one bead here, distance of separation as r, and of course this is also r, this is also r. And one can understand that this total angle is going to be 60, then this will be 30 degrees and this will be 30 degrees. What for we have taken that angle bisector, you can understand now. If I consider A and B are the beads having identical charges, so the charge on this one is Q, charge on this one also is Q. That's what has been given. Now masses are also M each. Then you can certainly understand this repels this one with some force. In turn, this repels this one with the same amount of force. When I consider its mass as M, you can certainly understand mg will be the weight of that bead which is acting vertically down. And what is the other force that it is experiencing here? That is force of repulsion between these two will now try to push this one that side. And what is the third force you can understand? The force over here is nothing other than the tension that is acting towards that point called center. So there are three forces which are going to act over here. That is the concept. What we now can understand in this particular case is what is this, the relation between these two we have to take. Come on, just look at this triangle carefully. I take this point as O and this point as C. I take from the triangle OCB. OCB I am talking of. What will be tan of 30 degrees? You can all understand opposite by adjacent. Opposite means I can take that one as repulsive force between the beads, and adjacent means I can take the weight over here. But all of you can certainly understand tan of 30 is nothing other than 1 by root 3. So you can now understand this is equivalent to 1 by root 3. So what can we write now? You can write that F of repulsion, that is repulsive force between the beads, is equal to mg by root 3. Now first let us write what is the formula for force of repulsion between these two. What is the formula? 1 by 4 pi epsilon naught Q1 Q2 by R square. Since both the beads have the same charge Q each, the product of those charges will be Q square. And separation distance between them is already given in the problem, that is capital R. So I now can write Q square by R square. This is equal to mg by root 3. But what I want is what is the charge on each bead. So what should we do now? Just write from this equation what is the value of Q square first. What will you get now? It will be 4 pi epsilon naught R square into mg. Look at 4 pi epsilon naught R square into mg divided by root 3. Now you can say from this one charge must be equal to root over 4 pi epsilon naught mg R square by root 3 as such. Look at this is actually the charge on each bead I have got after the calculation of it. And what are the options given? You look at the very first option is coinciding with this 4 pi epsilon naught mg R square by root 3 whole under root. This is in coincidence with the very first option given there. Therefore, answer for this particular question now will be A as such. So what you can understand here, once again look at please. He is talking about two beads which are in equilibrium over here, like he said. The distance of separation is given as R, but we know mathematically this distance will be R and this distance also will be R. They are the radius. radii of that particular one. So we can say this must be an equilateral triangle that is being formed. So taking this equilateral triangle, considering this angle as 30 degrees, that is angle bisector has been drawn over there. What is the value of tan 30 I have estimated? That tan 30 is force of repulsion between these two beads divided by the weight of this particular bead as such. If I just write its value, force repulsion, I am getting it as mg by root 3. But what is the force of repulsion between the beads? We know according to Coulomb's law, 1 by 4 pi epsilon naught q into q, that's q square, by distance of separation whole square. Then what can we write now? From that we have written q square, and therefrom I have estimated the value of q, which is root under 4 pi epsilon naught mg r square by root 3 as such. That is the concept. This is in coincidence with the first option, which is A, that is the answer for this question number 9. Let us switch over to problem number 10. It is also one of the very good models. It has appeared in previous papers also. A charge capital Q is uniformly distributed along the circular arc of radius capital R as shown. The magnitude of the force experienced by the point charge plus Q placed at the center of curvature is how much? He gave the constant of proportionality in this particular case as 1 by 4 pi epsilon naught. That is, anyhow he has mentioned that one as k. And the options are given this way: k q q sin theta by 2 by r square theta. The second option is given 2k q q sin theta by 2 by r square theta. And third option 2k q q cos theta by 2 divided by r square theta. That's the third option. And fourth option is given 2k capital Q small q tan theta by 2 divided by r square theta. That is what has been given there. Now what exactly the way we people is to proceed with this problem? A charge capital Q is uniformly distributed along the circular arc of radius r. He has just given us an arc like this. This is the one. It is now having, say for example, positive charge as given in the problem. How much charge that is there on this? He said it's given capital Q, that to positive charge he said. Now what we just have to understand out of this? He is placing here another charge, say plus Q. And you can all understand this is R, this is R, this total angle is given as theta in the figure as such. But what we people have to do in such cases? We have to consider a small element over here. I am just talking of a small element like this. What is the charge on this particular element? I take this one as dq. And you should understand now this is plus q, this is dq. Then won't there be a force over here as df, please? If you consider the total force over there is df. If I take this particular angle, what it is making with this as phi, then what will be this component now? df cos phi. And what will now be the component over here now? df sin phi. But every one of you can easily understand in this case, df cos phi values are being added up, whereas df sin phi values are going to be cancelled. When I consider another element over here, df sin phi comes to the other side, both are equal and opposite, thereby the resultant value over there will be 0. So what we can understand, df sin phi, that gets cancelled, no doubt. But what is going to be added up here? df cos phi will be added up. So what we just have to look into, what is the force over here first? df I write. It is 1 by 4 pi epsilon naught q into dq by r square. That is the concept what we have. So we can write this one like this. But in fact, 1 by 4 pi epsilon naught, in that problem, it is given as k. So let us write that k as it is. It can be taken k into q into dq by r square. That is the equation what we just have to think of as the force over here first. Now the question next, if you just look at how to just calculate the value of dq there. That's the point. How to calculate the value of dq means, what can we write now? Linear charge density. I just write. What is the linear charge density over here? Lambda, I can take this one as dq by dx. Now you can even understand that one, lambda is equal to dq by dx is the thickness of this element, that can be taken as r d phi. Now you can rewrite the same this way, dq is equal to lambda r d phi. This is the value of dq over here. So what I can write now in this case is df is equal to, now directly we can write k times q into dq, dq means lambda r d phi, whole divided by r square. Look at this one carefully, q dq by r square. dq I am writing this value by r square, one r gets cancelled. Then what is left over? kq lambda d phi by r. But we know pretty well what will be the value of df cos phi, because df cos phi values are being added up. That's what I have already mentioned in the beginning. df sin phi is getting cancelled, but df cos phi, all the values of df cos phi are going to be added up in the downward direction. Therefore, I can write now what is df cos phi. df is this much. Cos phi I can write. So it is k q lambda cos phi d phi divided by r. So I can rewrite the same this way. Now this is actually k q lambda by r cos phi d phi. That is the equation what we are getting. That is the effective force. So what is this effective force over here? This, if I consider it as effective force, right, or effective force, if I take, that now is going to be this much. That is df. If I want f out of it, what will now be the value of force we want? If we want the force to be calculated there, we need to integrate the total thing now. while integrating, what is it we have to take? You definitely can understand, if I just make this one into two equal halves, this angle will be theta by 2, that angle also will be theta by 2. Then how to calculate the effective force now? It is integral between minus theta by 2 to plus theta by 2. This value, whatever we are getting, that is k q lambda by r into cos phi d phi. I hope this step is clear to all of you. Then what are constants over here? You take them out. K q lambda by r. Right. Integral minus theta by 2 to plus theta by 2 cos phi d phi. You can now understand this one carefully, that this becomes k q lambda by r into sin phi between the limits theta by 2 with negative sign to theta by 2 with positive sign. So you can write this one sin theta by 2 minus sin minus of minus plus sin theta by 2. So what will you get now here? 2kq lambda by r into sin theta by 2. You will be getting that value there. Okay, if you look at carefully, what is this value of lambda now? Lambda is nothing other than the value of q by r straight away. If I write that value over here, this now becomes 2k q into q by r square into sin theta by 2 as such. Look at that equation carefully. And of course we know well that value of q by r theta we people used to write it for lambda. Therefore one more theta comes over there. So what is the corresponding equation? Look at now, 2k q by r square theta into sin theta by 2. Which one is now in coincidence with this one? You try to understand. 2k q sin theta by 2 by r square theta. Look at all the four options now. The second option is exactly tallied with the same. Then what can we write now? The answer for this particular question is going to be B now for us. Only thing you should understand out of this lot is how best once again we take a small element of thickness dx, having a charge dq, and just calculating the value for that in terms of df and estimating what is df cos phi. That df cos phi itself is going to be the effective force. To get the total force due to the entire charge on the arc, we have to integrate that one between minus theta by 2 to plus theta by 2. That is actually the concept what we need to remember over here. So once again, calculation wise a little lengthy, no doubt, but one of the best models what we people are having here. So all of you better remember the way of getting that result in this particular problem. One of the good models, looking a little lengthy, no doubt, but one of the best models what we people are having, that is problem number 10 in this order for us.